Hello, my friends and colleagues. Today we want to talk about how does the Passivhaus standard actually work? Because this is one thing that I've noticed. Um, Often, even people that have done the training already, they don't really understand what is the idea behind it. And that's what I want to give you today as an overview, how I at least see how the Passivhaus standard works, and maybe things that we can actually improve in the standard and in our practices to make the world a better place, because we don't want to tick just another box for achieving a passive house. We want to make sure that we are making a difference in our world. Like I always say, passive house is the first step. Step one, okay, I know that is underwear, but for me, it is step one. The first step is passive house, not passive house per se, but the idea behind Passive House. And that's what I want to give you today. So the crazy thing is, Passive House works for everything, everywhere. Okay, 99% of the time it works for every location, every design, and every building material. Passive House works everywhere. So how does it actually work? First, we have to know what is the outcome, and that is what is defined in the passive house standard. We have to find an outcome, and the outcome is a healthy and comfortable home so that we can drive in there. If we don't know our aim, we don't know how to work there, and we may even walk away from it. This is the reason why we need to define the aim, and that is this healthy and comfortable outcome that Passive House has defined based on science. Then, what the Passive House standard is doing is it tells us how much energy we are allowed to use for it. So, how much energy are we allowed to use to actually achieve the Passive House outcome? So here, that is really clearly defined. Maybe there are things that we can discuss, as sometimes it may make sense, sometimes it makes no sense. And then out of this, the defined outcome, the allowed energy to use, we have now our building methods, our design, that we have to make the decision what materials we use, how we define our building envelope, and what building services we use. And it's up to us to then achieve this amount of energy to achieve that outcome. This is the idea of the passive house standard on a really, really simple level. So simplified, harsh climate, thick walls; mild climates, thin walls. Harsh climates, we need to do more. Mild climates, we have to do less to have the same amount of energy consumption. Okay, so let's now go back to the outcome. What is the actual outcome that the passive house standard is defining? First of all, we are creating this healthy and comfortable environment. What do I mean by that? A temperature between 20 and 25 degrees, 24/7. That's the idea. If you're coming from the outside, from extremely cold into a 20-degree warm room, we say that is warm, that is comfortable, and we're feeling good. If you're coming from an extremely hot day into a room that is 25 degrees, then that is fresh, it's cool, and we're feeling good. So we're seeing already why that is defined. And we know by science that 98% of people are feeling comfortable in this range. But we can, in our design decisions, shift here as well a little bit. Yeah. Keep in mind, when we're allowing lower temperatures in the building, like 18 degrees, then the risk of mold and condensation is starting to be higher, because from 12.6 degrees to 18 is a smaller bridge than from 12.6 degrees to 20 degrees. So the risk starts to be higher that you're having mold problems if you're allowing lower temperatures. However, I wouldn't worry too much about if you're following the passive house approach, because there is so much room in our design that the risk is not there if the temperature drops to 18 degrees. So I wouldn't worry too much about it. Higher temperatures, if you allow higher temperatures in the building, what the standard even allows with that 10% overheating, that is a historical data figure. I wouldn't use that 10%. Never ever allow the passive house to overheat by 10%, except you're building an extremely cool and tempered climate. In that regions, it may make sense, but not in a climate like we're normally facing here in Australia, where the temperatures go up to 40, 45 degrees. A better way to actually find out if you don't want to have a cooling system and you say, no, my client is completely against cooling, he wants to live in a house that has no cooling in there, then I would set my temperature, so change the temperature range from 25 to 27, and then say we never want to go above 27. That would be perfect. If you say no, it's a bit too hard or too expensive, you may be going up to 28 and set your overheating percentage to 0 there. Then you're still fine. And then check at 27 and 26 how big the percentages are. And with this, you can gauge if this is now a good design or not a good design, or if you have to do more. If you're not using cooling, in my opinion, I would always put a cooling system into the building. This is not passive house now, what I'm saying. I would always put a cooling system into the building that can be operated with the energy I'm producing on the roof with my solar system. Yeah, if I'm building a home, not so important for offices and stuff like that, but like big buildings. But if you're speaking about a home, a residential building, we want to make sure that the building is able to cool, even if the grid is off grid. So if the grid is broken because of a power failure, because of a transformer blow up, or we had an extreme weather event or whatever, there can be events that, especially in extreme weather events, that the grid is failing. And now if it's hot, we're coming to a point where it's life-threatening if the temperature gets too high in the building. Has nothing to do with passive house. This is for every building. I would always make sure that the cooling demand, or the cooling load, better said, is able to be delivered with the solar system on the roof. Or uh, if you can't have solar in your place because it's completely shaded, then maybe have a spare battery in the house that could at least run this cooling system in a way that you can cool it for 24 or 48 hours or something. Normally, power failures are restored in a 48, 72 hours window. However, there are as well areas when big transformers are blowing, then we could have a problem that it's even for months without power in regional areas. Urban areas, I think we always get it fixed relatively fast, but it could be that there is a situation where small villages or single farms or so are out of electricity for a relatively long time, but normally they can produce plenty of energy on site. Okay, so this is my personal requirement, where we're going more to the smart plus building that I like to talk about. Then I say one requirement for health reasons is cooling that can be run with the system on site. That is what I would say is important. So temperature 20 to 25 degrees, cooling able to be produced on site. So in the case there's a power failure, we bring it down. That's my requirement. Then relative humidity between 30% and 60%. If you go below 30%, then our skin and everything is getting dry. And by that, we're letting bacteria and viruses more into our body. And by that, we're getting more sick. And above 60%, then we have the chance of mold growth and bacteria growth and things like that. That is far higher. So the repetition growth is more. That's the reason we want to stay in that percentage of relative humidity. So that's all defined in the standard. Then we're defining the surface temperature of the surfaces, and we have to make sure that the surface temperatures and the ambient temperature, so the room temperature and the surface temperature, that they're close together. Because if they're not close together, then we're having that feeling of a cold shoulder effect. So single glazing, cold day, your shoulder is going through the glazing, then you have that cold shoulder. We want to avoid that, because then we're feeling uncomfortable. So that's, did I forget something? Then the mold problem. thermal bridge-free design is not just an energy requirement to make the building more energy efficient. For me, it's far more the risk of mold. Yeah, we don't want to have mold in our buildings, and that's the reason we're building thermal bridge-free, because a cold spot is a mold spot. Thermal bridges getting rid of the cold spot, and by that we're getting rid of the mold spot. Yeah, so that's what we want to do as well. Additionally, we have obviously our airtightness system. The airtightness system is there to make sure that we have no condensation in our build-ups and that we're keeping the energy in and that the thermal insulation can perform. So that's more on the thermal side, but as well there could be mold growth because of the lack of airtightness. And that's the reason why we're having the airtightness system in there as well from a health perspective. Then as well, we have the airtightness and the surface temperature as well, so that we don't have a draft in the room. So we could have actually a draft from the inside to the outside if there's no airtightness. We stop that with the airtightness system. Or we could have a draft in the room circulating just because of the thermal difference between surfaces and the air temperature. So if that is too big, or from the lower level to the higher level in the room, then the air starts circulating, and that can give you that feeling of drafts on your feet and having cold feet. All that is defined in the Passivhaus standard. You don't have to worry about it. As long as you're following the Passivhaus standard, you're achieving this outcome, and then you're feeling healthy and comfortable in that building. Comfort is a health requirement. We're feeling comfortable when we are in a healthy environment. Soon we're feeling uncomfortable. Our body is telling us something is not right. First we feel uncomfortable, then it becomes unhealthy, then it becomes a health threat, and that is killing us. Yeah, so comfort is a health requirement. I think that's important as well to keep in mind. Then that's the outcome: healthy, comfortable home that you as a human can drive in. Extremely important for your home because you're spending 50% in there, and for your business owners, extremely important for your offices if you have people working in your office, because you will have far less sick days, and the outcome of an employee will be far better if they're feeling comfortable in your office. So there's as well an economical reason for you to build your offices that way. There's as well data existing, especially with LEED in the US. They have a lot of data on that that is amazing and tells you how much more can be actually achieved with high performing buildings. Okay, outcome clear, science, human body, it's the same in Siberia or the Sahara. Doesn't matter if you're in Hobart or if you're in Darwin. Our physical body is the same. Our core temperature is the same. Our needs are the same. Yes, we're having maybe a better resistance to heat if we're in Darwin and we are grown up in there, and we may have a better resistance to cold if we're in Hobart, but still we're in that 20 to 25 degrees. We are feeling comfortable despite being in Darwin or grown up in Darwin or in Hobart. So that is, it's just, that's how our body works. We're humans. We're all the same. We have the same body with our nuances that are different in personality and as well body functions and all that stuff. But that's the outcome. Let's now look to the energy consumption, what everybody talks about when we're talking about Passivhaus. That is obviously our 15 kilowatt hours per square meter, our energy, our thermal demand for heating and cooling of a building. If you're taking that 15 kilowatt hours for heating and the 15 kilowatt hours for cooling, combine them, getting to 30 kilowatt hours, putting now a heat pump on it with a COP of 3, then we're at 10 kilowatt hours that we actually need to bring to the building. And now with 10 kilowatt hours as a square meter, we need about 1 liter of petrol per square meter a year to actually condition that space in the worst case condition using a heat pump. Okay, so I brought that now together. The standard says 15 kilowatts for heating, 15 kilowatts for cooling. Together, 30 kilowatts. What's the maximum allowed in our Passivhaus building? Now we're banging in a heat pump that has 1 kilowatt of electricity in and gets 3 kilowatt of conditioning out. Now that 30 kilowatt hours divided by that 3 is now becoming 10. So we need 10 kilowatt hours of electricity, and they are roughly 1 liter of petrol per square meter. So if we now translate that for a whole building, let's say we're having a 200 square meter building, then we need 200 liters of petrol. If we then say we have a 50-liter tank in our car, then we need 4 times to run to the petrol station to run this house for the whole year for the conditioning. This is the efficiency, or the worst efficiency that a passive house would have. This is now the energy consumption of a passive house maximum for the heating and cooling. So it's not a zero energy building that is often communicated. No, it still has a heating and cooling load, because with this heating and cooling load, it's more economical than actually going for fully zero energy building. And as well, because energy is theoretically available on site with solar, we can actually achieve that conditioning easy. So this is now the energy consumption. That's the standard. The other thing is the load, the 10 watts per square meter for heating. I wouldn't worry so much about that, especially here in Australia, as we're using split systems, heat pumps for conditioning. And there, that 10 watts are not so important any longer. That 10 watts are only important if you're using the ventilation system, heat recovery ventilation unit, to actually supply the fresh air. That is something I forgot earlier on the health side. Obviously, fresh air, CO2 level under 1000. It's not about the CO2. It's about all the off-gassing and odors that are in the air, and we're using the CO2 levels as a guidance. The CO2 at 1000 is totally safe, no problem. At 1500, we're starting maybe to get a little bit tired, but it's still safe. It's not killing you. So if you're living in your passive house and the ventilation system would be failing, we know it's not a problem. 4000, that's where it starts to be dangerous. But believe me, before we have a CO2 level of 4000, you will know it, because it will be really smelly and stinky, and you will open your windows anyway. And you can in a passive house. And then out of this, we're then designing our building envelope, and we're designing our services. And that's how the Passive House standard works. Hopefully this gave you a little bit a better understanding of it, or the way that I look at it. If you have any questions or any comments, please put the comments below. I would love to get back to you and answer your questions, because I'm here for you. I want to help you to understand this world of high performing buildings and building for the future better. Let's make a difference together. Love you. Talk to you then.